Okay, here we are at using systems of two equations. And we know in this textbook, anytime you see the word using, that's code for word problems. Basic approach you use for all these problems is the same. Understand the problem, put together a plan, find the answer, and please don't forget this. Does it make sense? You probably can't read this little cartoon. I'll read it for you. A train, this is the question he has on his math test. A train filled with math experts leaves Sacramento going 50 miles per hour. 42% on the train recommend traditional forms of teaching math, while 48% advocate a modern interactive approach. There is a 25-mile-per-hour headwind as the two groups wrestle for control of the throttle. How long before a student at point B is proficient in math? His response, blue. About where any of us would be, I guess, faced with that particular problem. We're going to do a quick review. One of the things we're going to do right here is determine which method works the best. Should we use substitution, or would linear combination work better? Usually you can use both, well, either one of them. But what is a smart thing to do? Go with the one that will yield you your answer in the most direct way. Since this one already has solve for y, I'd propose that we use a substitution method. We're going to take equation number 1, and instead of writing y, we're going to write y's equivalency in terms of x. So that goes right in there. Then we'll have 3x plus, we're going to distribute the 5 to both those terms. We'll have 10x minus, what's 5 times 13? 26 is what it's equivalent to. Well, I've got like terms now right here. I'm going to combine those, and I'm going to add 65 to both sides. My new equation here will be 13x equals 91. Is that right? Now, I think that will go in evenly. Let's see. 13 times 7. Yeah, that equals 91. So I'm going to say x equals 91 divided by 13, which is 7. So I have part of my answer already, 7. Remember, my answer is always a point with an x and a y. I'm going to use the simplest equation for me figuring out what y is. It's given to me right there. Y equals 2 times x, and I'm interested in x when it's 7, so 2 times 7, minus 13, so y equals 1. That's using substitution. Problem number 2, linear combination. It does seem that in this case, that would be the better approach. Agree? We could solve it using substitution, but I can see it's all lined up, and if I multiply my second equation through by a -2, I will be able to eliminate my x's. So I've got my first equation isn't changing. There are other ways I could have done this, which would have changed both of them. but I thought this would be easier. So I'm going to multiply every term on both sides by -2, which will give me negative 4x. That's what I was looking for. -2 times -2y will give me positive 4y. And -2 times 4 give me -8. Now I'm going to add. You know that's my preferred way of doing it. This will 0. When I add these together I get a positive 1y. Oh, this worked out nicely. So now I know that my y is 5, and I'll use one of these to figure out what my x is. I think I'll use that second equation. 2x minus 2 times y, in this case it's 5, so minus 10 equals 4. So 2x, I'm going to add 10 to both sides. X is equal to 7. So there's my point. So we've used both. It's a little review we've done. Using a system of 2 equations. There's 3 types of problems that your textbook covers: mixture, motion, and digit problems. If you want to stop now and use your textbook, you could work examples 1, 2, and 3. What you might want to do is follow along with this instruction. If it makes sense to you, good. If it hasn't quite gelled, go back to your text and work out those examples. We're going to go through a mixture problem first. At a school play, that's how many tickets were sold. We have adult tickets and children's tickets. That's what the mix is. So if I let A equal the number of adult tickets and let C equal the number of children's tickets, I have the 2 variables I'm going to need, because the question is how many of each kind were sold. Well, so as soon as I know what A and C are, I have my answer. Well, we're going to go back and look at these sentences and see if we can convert them into equations which use A and C. I know that in total we sold 129. I also know that we were only selling adult tickets and children's tickets. So the number of adult tickets, A, plus the number of children's tickets, C, must equal 129. We're told that the adult tickets cost $100. Oh, wouldn't that be awful? $1.50, and the children's tickets are just 75 cents. We also know that the total amount that was brought in at the ticket booth was $153. I know that we sold some number of adult tickets plus some number of children's tickets. I've already done that up here, though. In this case, I have to think about the amount of dollars that were generated by selling these adult tickets. It would be 1.5, wouldn't it? $1.50 per adult ticket. So I multiply the cost times the number of adult tickets, and I'll do the same thing for the children's tickets. So I do have, let's see, 2 variables and 2 equations. If you have 2 equations with 2 variables, you can always solve the problem. Now, I am going to convert this into fractions. I know you're going to be surprised by that because you've heard me say, I'm not that fond of fractions. But I was thinking of clearing the decimals here, and I decided I didn't want to do that because then I'd get this huge number over here. So instead I'm going to consider what would happen if I converted to fractions and tried clearing the fractions. What would I need to multiply everything by in order to clear the fractions? That's right, multiply everything by 4. And when I do so, I'll have 12 over 2, or 6a. I'll have 12 over 4, or 3c. And I'll have 152 times 4, yikes, which will be 608. I hope I'm right on that. Now I've got A plus C equals 129. So there's my system of two equations. I think the easiest way for me to go at this point would be to multiply this one through by -3 and get rid of my children's tickets. So I'm leaving my first equation as it is, not making any change to that. The second equation, every term on both sides is going to be multiplied by -3. So I'll have -3a, -3c, and multiplying this by, I know I'm going to have a negative number. What's it going to be? 387. I hope I'm right. I actually don't like arithmetic. I like the mathematics, you know, the problem solving. But addition and subtraction, ugh. Okay, 3a. This will 0, exactly what we want. And this will become, I'm subtracting 387 from 608. And let's see, I had to borrow. Okay, let me just check that. 8. Yeah. All right. So my A is going to be 221 divided by 3. Now I'm really getting nervous. Will 3 go evenly into 221? I don't think so. Something's wrong. I better pull my calculator over. Make sure I haven't made an arithmetic error. First of all, this would be 3/2, and this would be 3/4. When I multiply by 4, this will become 6a, and this will become 3c. So I'm okay so far. On. Okay, 152 times 4. Make sure I did that right. 608. Okay, that's okay. And then I multiplied all of this by -3. So 129 times a -3, a -387, 608 plus a -387 is 221, and then you divide by 3. Well, I hate this problem. I must have had something wrong in starting it, because we know that they didn't sell a fraction of a ticket, so there's obviously something a little screwy here. All right, so this turns out to be 73 2/3 tickets. All right, I'll have to call it 74 tickets. There's something, maybe when they counted up their results, they were off by $1 because, oh, well, we'll get back there in a moment. If A is 74 and we sold 129, then C must be equal to, this was my A, C must be equal to 55. Sold 55 children's tickets. 55 children's. Now when you give your answer, give it without any variables. And 74 adult ticket. So there's our answer. A motion problem. A car leaves Chicago traveling west. Okay, I'm just going to make a note of that. Traveling west. And it's moving at 45 miles per hour. 3 hours later, so this was at time 0. At time 0. Then 3 hours later, at time, oh, see, I didn't wait long enough between doing this and doing this, and it wants to draw a line for me. 3 hours later, another car leaves Chicago, traveling in the same direction, west, at 60 miles per hour. How far from Chicago will the faster car reach the slower one? So at what point do they catch up with one another? So if I call this car 1, and this car 2, so here we're talking about the rate for 1 equals this, and the rate for 2 equals this. And we're going to say that the distance we're looking at, which is a distance from Chicago, they'll both be the same distance from Chicago. What do we know about the time? Well, we know that for the first, the time, well, we don't know what it is, do we? It's going to be, I'm going to say X. And for the second one, it's going to be X plus 3. We know it will have traveled, oh, what am I saying? X minus 3. X minus 3. It's traveled for 3 less hours, right? What else do we know? We know that distance equals rate times time. I've got 2 variables here, haven't I? I don't know the time and I don't know the distance. The only thing I do know is the rate. Well, let's try writing it out. Distance 1, I can just call it D, can't I? Because D1 equals D2. But anyway, distance 1 equals the rate it's going, 45, times the time, which I named X. And distance 2, which is exactly the same as distance 1, we're going to show that in a minute, is 60, but the time is going to be 3 hours less, as it started 3 hours later. And I'm going to set these equal to each other, so I've got 45x equals, and I'm going to distribute this, so I get 60x minus 180. If I add 180 to both sides, 45x plus 180 equals 60x. And then if I subtract 45x from both sides, I get 180 equals 15x. So my x is equal to 180 divided by 15. And what will that be? Well, let's see. 180 divided by 30 would give me 6, right? So I'm only dividing it by half as much, so it's going to be 12. Is that true? X equals 12. And we know our unit of measure is, oh, I bet you were trying to tell me that. Our unit of measure is kilometers per hour. How far from Chicago will the faster car catch the slower one? Well, I'm showing that my time is 12 hours. Is that true? Talking kilometers and hours. So the distance at, let's use this equation here. The distance is going to be 45 times 12. The distance will be, I'll pull my little calculator over here. Turn it on. 45 times 12. Distance is going to be, in kilometers, 540 kilometers. Now we're going to ask ourselves, does that make sense? 3 hours is a lot of time that first car has left in advance of the other. It can cover a lot of miles. And it can cover a lot of kilometers. So it has, before this one even starts, it's already covered, what is that, 135 kilometers. It's gone that far from Chicago before the second one even gets started. And then this one is faster, would have to be, but not horrendously faster, so I think that makes sense. A digit problem. The difference between two numbers is 3. And we want to know what the numbers are. So let me say x equals one number, and I'm going to say that's a smaller one. And y is the larger one. If the difference between two numbers is 3, how do I set this up? I say y, the larger one, minus x, the smaller one, equals 3. The other sentence here, 3 times the smaller, so that's going to be 3 times x, plus 2 times the larger, plus 2 times the larger, is, and we know we always write is as an equal sign, 31. Now I could do linear combination, but since we've already demonstrated that, let's convert this into something we can use for substitution. I'm going to add x to both sides. It has this lovely property of not having any negatives in it either. I like that. So now I'm going to use the second equation, 3x plus 2, and instead of writing y, I'm going to write what y is equivalent to. which is right over here, x plus 3. Now I can solve this. I'm going to, remember we always deal with the parentheses first. Order of operations is always an important concept. 3x plus 2x plus 6 equals 31. I have some like terms that I can combine. I can subtract 6 from both sides, and then I will have all my x's on one side. That will be 5x's, right? 5 times x equals, I subtract, and what do I get? 25. Oh, this is looking good. So my x is 5. That's part of it. I can say the smaller number is 5, and the larger number is the difference between them. If you add 3 to the smaller one, there's my answer. I don't think I even assigned this one. This was number 34. But I left it in this lesson because it was a great demonstration. Here was an error I did. And I thought I would use it as an example here. I had taken a problem which had Union Station over here and Central Station over here. And I had tried to solve it in front of a class without consideration of the fact that they were going in opposite directions. The problem we had earlier here, the motion problem, they were both leaving from Chicago. And that probably, when I did this next problem with another class, it probably threw me off because I'm thinking of going from the same city. Didn't read the problem correctly. But if you check in your book, number 34, these trains are not both departing from Union Station. We have one going from Union, the other one going from Central. Makes all the difference in the world reading the problem. Well, we are done for today. If you think you need a little more practice with word problems, well, you're going to get it in your homework. And you can also check out those exercises that I recommended to you. There you can see those worked out step by step by step. Number 1, number 2, and number 3. That's in your textbook. That's totally optional. In this course, some things are required, but you have more flexibility than I have ever given students before. Have fun.